Hi there, welcome back to the formulaic approach. In this video, we are going to talk about electric potential. Now, before I begin to talk about electric potential, one thing I want to first do is to clear the kind of misconceptions that students have about electric potential and electric potential energy. Sometimes students tend to confuse them. Now, there are two different terms. We have electric potential and electric potential energy. Now, electric potential is denoted by V. That's the first difference between them. While electric potential energy is denoted by U. Remember, that's the same letter we use in thermodynamics here for energy, internal energy of a system. So electric potential is V, electric potential energy is U. Now, so if I put V here and put U here, now what's the difference between them? Now, by definition, we say that electric potential is the work done per unit charge brought from one particular point to a reference point. Actually, that is electric potential difference. Okay, but so that we'll talk about it as a case where the charge is moving from a point of no potential, which will be to that reference point, infinity. I'll explain why that is the case. To the reference point, that point of no potential will be infinity. So from the work done in bringing every unit of charge, any unit of charge from that infinity to a point is called electric potential. But electric potential, so I mathematically write it as electric potential V is the work done per unit of charge brought from infinity to the reference point, while electric potential energy is that work done itself. The work done is seen in terms of the electric field. It has nothing to do with the charge. That is one thing you should know. The electric potential energy is seen in terms of the electric field. Okay? Now, so it is the work done itself in bringing a charge to a point. But this one is the work the work on each charge, work done on each charge. That is the electric potential. Each work done on each unit of charge, that's what I mean, each unit of charge. So it means essentially they will also differ in the unit of measurement. So this guy, work done is measured in joules. This guy, charge is measured in coulomb, okay? Or electric potential is also measured in volts, named after Alessandro Volta. You have seen my video on electrostatics, I've talked about him. The unit of this one, therefore, electric potential energy will be joules. So now let me now differentiate between them essentially so that you will understand. I'm going to use the classical locus classicus. Locus classicus, that's the classical example we use. The classical analogy we use. Now you see, this guy can be related with the gravitational force, the gravitational field of the Earth. Now let me ask you first, where's the direction of gravitational field of the Earth? If this is our ground, okay, this is the Earth's surface. Now any object, if this object is on the ground, this object, as it is on the ground, its potential energy, we call it gravitational potential energy, is zero. Okay, so why is it zero? Because the work done on this body by, where is the electric field pointing? In this our Earth. This is our Earth now. So this is this ground I'm standing on. So let's say this is me now, for example. So the work done, so let's draw me actually. So this person is experiencing gravitational pull of the Earth. So the Earth is trying to pull this object towards itself, makes sense, and the direction in which it is pulling is what? Towards down. So every object that goes up must surely come down. So this body experiences it as weight. Okay, so now if this body, so the gravitational potential energy of this body is 0. Now if this body moves up, it is moving against gravity, against the field of gravity, because the field of gravity is moving down. So it means that the work done by the field of gravity on this body is always towards down. So it means that down is positive for this body. Does that make sense? But if this body moves up, let's say for example this guy jumps up to this point, it gains potential energy. This body has gained potential energy. Why? Because it has moved up. So but since we describe it in terms of the field, we describe potential energy in terms of the field, this case gravitational field, it means that the work done by the field is going to be the negative of the energies, the potential energy stored in this guy because of its position in this field. It has moved up against the field, right? So we say that the field has done negative work on this body. So the work done, that's why there is negative here. Exactly. That negative indicates that the work is being done against the field. Direction of field is down. So once this body jumps up, then this body stores up potential energy, which is U. And that potential energy U is equal to negative of work done by the field. Do you see that they are equal and opposite now? Do you understand now? So the work done is going to be negative of the field, and the work done is going to be negative of the field, or the field's the work done by the field is going to be negative potential energy stored in the body. Does that make sense now? Good. So in the case of electric field potential and electric potential energy, it is the same. Now if the electric field is pointing, let's now say this was the electric field. Electric field is also pointing everywhere on this board. Electric field is pointing downward. But of course, you know it's not acting on a human now, or on the body with mass. Now we're talking about charges now, okay? Charges have mass though, but I'm saying we're not talking about the mass now. We're talking about the field of electricity. So let's say this charge, there's a charge here. There's a charge on the ground here. So this is now E field, okay? This is no longer gravitational field. This is now E field. So in this case, we'll be talking about electric potential energy now. So once this object is as far away as possible from the field. Oh, sorry, I didn't even talk about that first. Now you see, this is it depends on the charge of the body, okay? So let's say this electric field here is from a point positive charge somewhere. So there is a point positive charge somewhere that is sending electric field in this direction. So electric field is towards here. So if these are point charge, this is our point charge. If this point charge we have chosen is a positive charge, if this point charge that has been chosen is a positive charge, it means that the direction in which the field is acting on this body is away from the charge. So for the electric field potential energy on this board stored in this charge to be 0, then this guy has to be at infinity relative to this field. Exactly. So when this guy is at infinity, electric potential energy stored in it is 0. It means that the energy, the electric field is doing positive work on it, meaning that it is moving it to the point of its lowest energy. Substances tend to move from point of low energy to point of high energy to point of low energy. They always want to make their energy as low as possible. That is why this body, if I just remove my hand from this body, where it goes is down, because the energy by virtue of its position above the ground is high, so it has potential energy. So this same charge will want to be pushed away as far away as possible. Is that clear? Because it is positive charge. So now, what if a force from somewhere this is used to move this charge now to a point around here, to this point. So our charge is now here in the electric field. So where's the direction of movement? Here. Actually, the force must move it slowly such that it doesn't impact velocity on this thing, because once it moves speedily, it has is no longer electrostatics. So since we are still talking about electrostatics, charges at rest or charges that have very slow motion, such that we count it as almost at rest. Is that clear? So now that force has to move this body against the field. So since the force is moving this charge against the field, then the electric potential energy U of this charge is going to be the energy stored in the charge, and it will be equal to the negative of work done by the field on the charge. Is that clear? Negative of work done by the field on the charge. Why? Because the field is doing negative work on this charge. Why? Because the field is allowing it to move against the field. Do you understand now? A force is bringing it to be moved against the field, so that the electric potential energy stored on the body is going to be negative F times the distance moved. Does that make sense? Or U becomes, remember in electric field we have that F is equal to E, the electric field, times the charge, right? So we know that it becomes negative EQ times R, or EQ times D. Is this clear? All right. Then what is now the electric potential? Electric potential is now the work done per unit of this charge, that is brought from any point here, point 0 in this case, which will be our infinity with respect to this field, from that infinity to this point. Is that clear? All right. So that is the difference between electric potential and electric potential energy. Now let me now give you some points that you have to know about electric potential and electric potential energy. So of course, one first thing you see from this my equation that I wrote here is that electric potential energy, let's talk about electric potential energy first, since I already wrote the equation there. Electric potential energy is directly proportional. Now, you won't say that it is directly proportional to the work done. You will say it is negatively proportional. So directly negatively proportional. If I say it's proportional, it means it's directly proportional. Exactly. So it's negatively proportional. The electric potential is negatively proportional to the work done by the electric field on the charge. Remember, the work done, the electric potential energy, is seen in terms of the electric field in this case. Is that clear? So that is, it will be the energy stored in the charge, but is seen in terms of the electric field, so which means it's the negative of the electric field, negative of the energy, negative of the work done by the electric field. Now, so it means that this U, change in U, is equal to the negative of work done. And recall that the work done in a charge is EQ times distance, which could be D or R in this case. Then this guy becomes U, which is minus EQR, like we have said here. Now, there's also one thing. Both electric potential and electric potential energy, they are scalars. Both of them are scalars. None of them is a vector. Is that clear? So now, what's the next point you must know about electric field or electric potential or electric potential energy? So I've said that they are scalars. Okay, both are scalars. Both V and U are scalars. Now, the next thing you must also know is that electric potential energy or electric potential is, we've said, is directly proportional to this. Electric potential energy or electric potential. Well, let's talk about electric potential. Electric potential is can be gotten or can be derived. Let's use derived. I like derived from electric field. From electric field. Remember, E field is vector. Electric potential is scalar. From electric field by integration. And what do we integrate? We integrate the magnitude of the electric field, integrate the magnitude of the electric field over the distance moved. Integrate the magnitude of electric field over distance r moved in the field. Is that clear? All right. So then I'm going to show you that mathematically. Is that okay? So that we say that V is going to be the integral of E field dr. Each unit of distance covered. Is that okay? We are covering little distance. Okay. So this is the way we represent it. But remember, it's going to be negative E dr because we said the electric potential. Okay, I've not showed you this before. I didn't show you that electric potential is directly proportional to the distance. Let me put that here. I've not mentioned that. So let's put that down. That electric potential that's 0.4 now. Electric potential is directly proportional to the distance. Okay, so what that means is this. Let me just show you that. You remember that we said V is work done per unit of charge, right? So V becomes work done is force times dr, right? So over Q. And remember that F is EQ times R. Either whether it's dr, every little distance covered, or the full distance over Q, right? So Q takes care of Q and V equal to ER. So electric potential is very proportional to distance. So just like electric gravitational potential, this marker here is at a higher potential than this one. So this one has a higher potential energy. It's storing a higher potential energy than this guy. Or we say it is at a higher potential than this guy. Does that make sense? All right. But those two terms are different, which was what I just showed you. All right. So since we know this, electric potential can be derived from electric field by integration. Then it means that electric field can be derived from electric potential by differentiation. Exactly now. It can be derived from this by differentiation. All right. By the time you bring more equations, do this further. There's something that came to my mind now. You will begin to get things like V equal to E. Remember that E is KQ over R squared, right? Then dot R. R takes care of R and V equals KQ over R. This is the standard equation for V in electrostatics. Is that clear? V equal to KQ over R. So this one makes people confused that how do you say that electric potential is directly proportional to distance? You see, they don't understand that is seen in terms of the field. Electric potential is seen in terms of the field, right? So in the field, the electric potential is directly proportional to the distance from the field. Is that clear? All right. And I'll still talk about that due to a point charge. Is that clear? Now, what if I have multiple charges? So this one is just saying that I can get E by taking the derivative, E field, by taking the derivative of voltage. Okay, so that I have E of electric potential, E becomes negative dV dx. Given that x is distance here, is that okay? Distance, or dV dr, either ways. So by the time you take that, E becomes d kq over r, or kq over x in this case, dx. So by the time you do this, this becomes E becomes dd's kq is constant, so by the time you differentiate this, so it becomes 1 over x, differentiate 1 over x, you get 1 over x squared. That is kq over x squared, which is exactly what we get, what we brought here. Do you understand now? So you see, you can get electric field by differentiating electric potential. All right. Now there is one more thing that I still need to show you. I'll still have to explain. There's something you must still wait till the end of this video for. I want to explain what electric field due to a point is. Okay, and how we calculate that. Now, you see, if we bring this guy here is for when we move from infinity, I showed you. So that is, this is the electric potential when we move from to a particular point, a particular distance from infinity. Is that okay? So this is the electric potential from infinity to this point, infinity to this point. So this is what gives us E integration of E dr. So we are moving from infinity to this point. So that is from infinity to r. Is that clear? So what if we now want to calculate for a particular point between 2 points? So electric potential due to 2 points now. Due to a point, electric potential due to a point. So what we'll do is we'll pick a final and an initial point, right? Okay, so electric potential V initial minus V final. Okay, that is going to definitely be the negative integral of E dr from initial point to final, not infinity to that point now. This one is infinity to the point, such that by the time you do that, infinity will become 0. 1 over infinity is 0, right? It tends towards 0 by the time you integrate that. Okay, so by the time we do this, so the change in V, which is V initial minus V final, becomes, to integrate this, it means that we'll take E dr. Okay, so what is E? E is kq over x squared, or r squared in this case. So what we'll have is negative integral of from I to f of kq over r squared dr. If you want to integrate this, so the change in V becomes a negative integral. So let's put negative outside. Now this guy is constant, so we have kq, makes sense? Kq, then into bracket integral of 1 over r squared, so between I and f dr. So this is what we want to solve, right? This is what we want to work with. All right. I'm going to, okay, let's see if we can still write it here. So change in V becomes minus kq for, let's start from this guy, we are subtracting this from this. So let's start from f. F becomes, by the time you integrate r, 1 over r squared, let's do that here. 1 over r squared, it means r is power minus 2. Increase by 1, then minus 2. Minus 2 plus 1. Here you get r is power minus 1. Here you get minus 1. So it becomes minus 1 over r. So we bring it here. F becomes minus 1 over r initial. This for final, sorry. For final, then minus the other case, we'll get minus 1 over minus for initial now, I want to subtract initial minus 1 over r. If you don't understand integration, make sure you see my video on integration, okay? R final, okay? By the time you know, work this out, do the math, what you'll get is this. What you get is change in V becomes minus KQ into bracket minus 1 over RF minus over R final plus 1 over R initial. Is that clear? Minus times minus. Minus and minus, minus plus. So by the time we arrange this, change in V becomes minus KQ into bracket 1 over R1 initial minus 1 over RF. Okay? So by the time we now bring this in, our delta V between 2 points becomes K minus KQ over R1 plus 1 over KQ over RF. Okay, so eventually change in V becomes plus KQ over RF minus 1 KQ rather over RI, R initial. So you see it became positive back such that we're subtracting from final to, we are subtracting initial from final. So this is the electric potential between 2 points. Now, what is the consequence of this thing? Now the consequence is this. What students don't understand that I was talking about is that when I have a battery, for example, if you have a battery, the electric potential is not just the work done in bringing every unit of electron from negative to positive charge, positive pole. Now you have to see that in terms of both inside the battery and outside of the battery. Exactly. So inside of the battery, chemical forces move electric charge from negative. The forces move charges, yes. Negative charges, they move them towards the negative pole, and positive charges, they move them towards the positive pole. That's one thing you first know, okay? If you don't understand that, see my video on the electrochemical cell, okay? I'm going to release another one soon because that one that I made has been long, so I want to remake another one. But I'll try and link that one in the description. So you see, so because of that, there is the positive end that we are moving positive charge to has a higher potential than the negative end. Is that clear? So what will happen is that the moment you connect your battery, the circuits now begin to do work on the charges by bringing them from positive to negative. By bringing positive charges from positive to negative, which we call current. Is that clear? So the potential difference across the two ends is now the work done in bringing those positive charges to negative. Is that clear? All right. So another thing I wanted to say is this. If I have a point positive charge and I bring a negative charge around it, now as this guy is moving, let's call this place point A, let's call this one point B. As this guy is moving from point A, if I push it, if I use a force, a particular force, to push it towards here, the potential energy of this charge will drop. Is that clear? Because where does this guy want to naturally move? It wants to move naturally towards the positive pole because of attraction, electrostatic force of attraction. Unlike poles do what? Attract. So this guy naturally wants to move towards here. Then if I now use force to bring it from here to this point here, to a point C here, what will happen is that the potential energy will increase. But if it comes here, the potential energy of this charge will do what? Reduce. Why? Because this is the direction in which it naturally wants to move because of its nature. But to this point, it will take more force to bring it here. So because of that, the potential energy will do what? Increase at point C. Is that clear? So we say that this guy is at a higher potential at point C and at a low potential at a point D close to point A. Is that clear? Good. So what if what if it was a positive charge I was now bringing? What was the positive charge? So we want to bring a positive charge to point C. The positive charge is point B. So let's call this point B initial because it took energy, it took some work. We had to do some work in bringing it from infinity to that point. Is that clear? Now, if we bring it from infinity to this point, now, it took some energy. But let's not say we want to bring it from here to here. The electric field of this guy is radially outward. It means that this guy naturally wants to move out. So it means that to bring it from B to a point D here, to bring it here, you have to do a lot of work, which means that the potential energy of this charge will increase at point B. But if you bring it here, this guy, at this point, the potential energy will do what? Reduce. It means that point C is at a lower potential than point D, while point D is at a higher potential for the charge than point C. Is that clear? All right. I hope that is very clear. The last thing you should know about electric potential is that electric potential due to multiple charges is gotten or is derived by the arithmetic sum. By the arithmetic sum of all the potentials. Yes, sir. So of all the potentials, of all the electric potentials, is that clear? That is, because it's scalar, what you simply do is what? Scalar addition. But you know that if it's for electric field due to multiple charges, you have to do vector addition. So for this one, scalar addition, just add all the V's. What that means is that if I add V due to V1, V2, V3, V4, as you have it up to Vn, to get the V, just add V1 plus V2 plus V3 plus, is it clear? All right, so that will be the end for this video. In this next video, I'm going to talk about electro. Maybe I'll even talk about battery now, what happens in the battery. God bless you as you subscribe and share the video with your friends.